The next speaker is James Morris. So I see you are already ready. So just go ahead.
My name is James Morris. I'm a student at Francis Marion University. I did my research on optimized multilayer structures with tunable materials. My mentor is Dr. Georgios Varonis, and we also did work with his previous PhD student, Xinglong Yu. So I am adding on to a project that was completed by Dr. Georgios Varonis, his former PhD student, Xinglong Yu, Dr. Jonathan Dowling, Dr. Yin Huang, and a previous RU student, Corey Mattias. They created a C program that used hybrid optimization algorithms coupled with the transfer matrix method to optimize material composition and the layer thicknesses of multilayer structures. Their project has applications in solar voltaics, photo detection, radiative cooling, and imaging systems. So, for the first 4 weeks of my research experience, I spent time trying to recreate the results that were previously found in their paper. So here is a plot of absorption as a function of wavelength given in the paper on the left, and on the right is the same plot that I used using the same parameters mentioned in their paper. And then if these are plotted together, you will see that they pretty much perfectly coincide with one another, and I was able to get the results I was expected to get. So after I figured out how the code worked, I began trying to implement my portion of the project, starting with the implementation of phase change materials known as germanium antimony telluride, or GST for short. With this phase change material, I am trying to optimize the absorption ratio between the crystalline and amorphous states of GST. GST changes phase when it reaches its crystallization temperature of 160 degrees Celsius, and its melting temperature of 600 degrees Celsius causes a phase transition to amorphous. Typically, these phase transitions are induced using pulsed laser light to momentarily heat up and melt the surface of GST to cause a phase transition. So, where does this data actually come from? Dr. Varonis provided an article that had this image here on the left, which I then used an online tool known as WebPlot Digitizer, which was used to extract numerical data from a plot of the real and imaginary parts of refractive indices as a function of wavelength. This image in the top right, or on the right, this image on the right is the numerical data that was extracted from this graph using WebPlot Digitizer, and it, as you can see, has the name of the material, the number of data points, the wavelength in micrometers, the refractive indice, the real part of the refractive indice in the middle column, and the imaginary part of the refractive indice on the far right. So with that, go to the next slide. So using the new data for each phase of the GST material, a plot of absorption as a function of wavelength was created. I was able to generate multiple 5-layer structures, which showed me that the material was being read in properly, and I was also able to get this structure which utilized both the crystalline and amorphous phases of GST. So this was the most optimal structure that the code picked, and it used GST amorphous twice and GST crystalline once. So moving into probably week 7, week 8, a good majority of my time was spent learning the C coding language. I came from a Python background where I was accustomed to seeing code executed line by line, seeing it work, and it was fairly straightforward. But in this code, there was 28 different files that are all linked together and work together, so there was a little bit of a learning curve for me. So here in the top, figure 9 shows code that begins the simulation for 2 different structures, meaning the transfer matrix method is ran twice, one for the crystalline phase and again for the amorphous phase, thus requiring a need for 2 different simulations or structures. And here in the bottom, figure 10 contains one of the structures called by the routine in figure 9. This routine specifically changes crystalline GST to amorphous GST. A very similar routine was written for switching amorphous GST to crystalline GST. We chose to only consider 2 structures, one containing amorphous GST and the other containing only crystalline GST. And here on figure 11 was the run log to show that it was doing what it was supposed to do, beginning here at the very top represents before the routine is executed, and then end representing when after the routine was executed. 4 was the unique ID assigned to, I believe it was crystalline, GST crystalline, and 3 was the unique ID assigned to amorphous GST. So after the routine was ran, we ended up having any incoming crystalline GST that went into that structure or into that routine was turned into amorphous. All right. So I'm not sure if I'll be able to get this video to play, but this has applications in optical switches, which allow you to switch optical signals without needing any sort of mechanical input. You can apply a voltage, apply heat, whatever your material requires. GST specifically requires a change in temperature. And it also I showed this video last time, I can't get it to play, but basically what privacy glass is it's a transparent glass-like material that when a voltage is applied, it becomes opaque instantly. So I also believe this could have applications in industry if the user wanted to input specific absorbance or transmittance values for the program to follow or create a tunable material. They could do so simply by editing the fitness function located in the user.c file to fit whatever they need. I believe this could save money as well as time in the industrial process, rather than experimenting with these multi-layer structures and trying to get the most optimal coding or whatever it may be. You can put in what transmittance and absorbance values you want into the fitness function, and you'll get returned the most optimal structure based off of physics. Moving forward, we weren't quite able to finish, unfortunately. I would like to do a little more testing of the implemented routines and then ultimately change the fitness function to actually optimize the on-off absorption ratios between the crystalline and amorphous phases. And it's a little hard to interact with right now. There's not a lot of comments. Didn't mean to do that. I'm sorry. There's not a lot of comments, and it's a little bit hard to edit the fitness function. It's hard to implement new routines. So it'd be nice if we could make that a little more user-friendly. And I plan on doing that hopefully in the next week or so before this fall semester starts. And for my acknowledgements, I would like to thank my mentor, Dr. Branas, for guiding me throughout this RE process. He was extremely meticulous, and he kind of really helped me understand the research process and that I should always test anything I put into the code multiple times. I also had a great pleasure working with Shenglong Yu. His helpful advice really helped me start out in this RU program. Without it, I don't know if I would have been able to even run my program at the HPC. I'm also very grateful to Dr. Moreno, who organized the RU and kept up with all of our meetings and kind of helped all of the RU students get together and have our own conversations. I also like to thank LSU Center for Computation and Technology for allowing me this opportunity. I know that it will provide an invaluable contribution to my academic career, as well as the NSF for funding this experience and making it possible.
Okay, you are very welcome, James.
Those are my references.
Questions? Yeah, I have a couple of small questions. In the figure you show with the structure, you have 3 layers of the material. So you consider all the possibilities, the 8 possibilities that, you know.
This right here?
Yes, I mean, you show a figure that you have 2 amorphous, another kind of layers too, but you have 3 layers, 2 amorphous and 1 crystal. I mean, in your structure, you have multiple, yeah, that. Yes, you are right. So
Okay.
do you consider the 8 possibilities that they could be, you know, the top 1 can be amorphous or crystalline, the middle one?
Okay, I understand. Well, the code actually, it uses a combination of different optimization algorithms to find the most optimal structure. And these are, if I go back, I still have the same, I'm sorry, all these transitions make it really hard to navigate. So I still have these same materials that were used in the original code because I didn't want it only be a GST material inside of it, because then because you don't really want to have GST amorphous and GST crystalline in the same structure. In that figure that I showed, it had both, and that was really just me testing to make sure the materials actually loaded in properly.
Okay. No, but then you answered my other question. That was, how do you make the switch if you have amorphous layers together with crystalline?
Right, and that's what we still have to test.
But in your structure, all of them will be amorphous or crystalline.
Right. So we're gonna what we're trying to do is optimize the absorbance ratio between the on and off states or the crystalline and amorphous states.
Okay, I understand. Thank
you. One structure would have, like, say, silicon, germanium, hafnium dioxide, and then just GST amorphous, and that would be, say, the on state. And what we had to do was make it so that it didn't try to put crystalline materials into that structure, because then it would be on and off at the same time, and that doesn't really make sense as of right now. In the future, that could be useful, but right now we were just trying to make it so it was only using 1 GST material per structure. So we're actually generating 2 structures. That's what's going on in this top part in figure 9. We're running through the transfer matrix method twice, which allows us to generate 2 different structures, one primarily using amorphous and the other materials used in the previous code, and the other using crystalline, as well as the other materials used in the previous code. And then we are going to adjust the fitness function, hopefully in the next week or so. I feel like we're pretty close to maximize the absorbance ratio between those 2 structures.
Okay. Any other question, comment, suggestion? Okay, there are no further questions left than James.